a talk by a postdoc in John Jenks's lab, Dr. Eric Mitchell. He'll be talking about assessing factors that influence individual and population level morphometrics for captive male white-tailed deer, so we're all looking forward to that. And this week we're very pleased to have Dr. Steve Chips with us from the USGS co-op unit here on campus. Steve comes to us from a bachelor's at Davis and Elkins College, a very small liberal arts school in West Virginia, and I did have to look it up. A master's at West Virginia University and a PhD at University of Idaho. His main research interests are in the feeding ecology and energetics of fishes, and today he's going to talk to us about mercury in fish, specifically mercury in the environment, implications for humans and fish. And I will pass over the mic to Steve. And all our remote folks seem to be able to hear today. Good.
Well, thanks, Josh. Before I get started, I'd like to have someone make an introduction. I saw Anad come in first. There he is. Anad is a Fulbright fellow that arrived a couple weeks ago and joined us in the department. And so Anad, maybe you could briefly give an introduction.
Yeah, I'm Murugananda, basically come from India, Dehradun. I work for Indian Council of Agricultural Research. Like USDA here, we have got Indian Council of Agricultural Research. I work there for fishery science. And here I have joined Dr. Steve as a Fulbright scholar. I'll be here for 18 months working on fisheries and land use change and all that. And it's good to be here and good to see all of you here, and we'll have a good time. Thank you, one and all.
Thank you. Before I get started, as Josh mentioned, we'll be talking about mercury in fish today. How many people eat 2 meals a week of fish or shellfish? Raise your hand. See, this is why the fishing is so good in South Dakota. Okay, I'll come back to that in a little bit. Let me get that over there. All right, so I'd like to first thank a few people who've worked with me over the years on fish and mercury issues. Former PhD student of mine, Trevor Selch, is in Montana these days. He's the aquatic toxicologist for the state there. Carrie Ann Mayer, she works for the USGS now, worked with us for a while. And then 2 Game Fish and Parks employees, Bob Canton, who's at the Missouri River Fisheries Center, and then Dr. Brian Blackwell. Brian is up at Webster in the GFP office. So I always like to start out by talking about the sources of mercury, because there's a natural biogeochemical cycle to mercury in the environment. Through oceans, volatilization of oceans, the weathering of rocks and minerals releases mercury. And then, of course, volcanoes, volcanic eruptions, are a huge source of mercury in the environment. And these are all natural cycles that occur. But as with any natural cycle, human activities often come into play and alter these cycles. And in the case of mercury, we've altered it by condensing it in point source pollution sources, the distribution of it in the atmosphere, and those type of things. And a variety of activities have been associated with mercury in the environment that are human altered. Agriculture, the production of fungicides. There used to be mercury in fungicides. There is no more. Manufacturing used to be a big source of mercury. The production of PVC, for example. Batteries. They used to use mercury in the production of batteries. Fillings. Maybe a few of you that have fillings in your mouth like me that have some mercury in them. But don't worry, I'll tell you why you don't need to worry about that. And then gold mining. The gold mining process back in 1800s, they used to use mercury to separate the gold from sediments. So those are all kind of things that have been remedied to a large extent. And then more recent sources of mercury have been from the combustion of fossil fuels, the burning of coal. When we talk about mercury, not too much concerned about the elemental form of mercury. This is what's in thermometers. When you broke a thermometer and your grade school teacher says, don't touch that, don't eat it, don't touch it, don't eat it. But it's not, in this form, it's pretty inert biologically, so it's not, from our standpoint, a health hazard to us. And in fact, if you go to Paris, the French like to play around with mercury. Here's a mercury fountain, as you can see. Some artistic work with mercury. But what we're concerned about mostly is the mercury that makes its way into the environment from these coal-fired power plants. And in this form, we call this ionic mercury. It's Hg2 plus 2 and 2, 2. And it's this form of mercury that makes its way in the atmosphere and then gets deposited across the landscape. And it's creating probably the largest issue for us, or it is the largest issue with regard to mercury in the environment these days. And if you think about it, of course, we've been burning coal for many, many years in the United States, North America, but all the coal-fired power plants that have come online in China, what's happening there with production of mercury, it's very significant these days. The problem with that is that's ionic mercury makes its way into the atmosphere, and then it ends up in places where we would never think it should end up, right? Because it deposits back to the landscape in the form of wet and dry deposition. So we start to see mercury problems in pristine lakes and streams and areas where there are no visible sources of mercury. So if we look at the evolution of the mercury problem since the mid-20th century at least, back then, many of these sources were industrial, direct, what we call these point sources, before we had legislation and mandates to not make batteries out of mercury and those type of things. But because it was a point source, in many instances, the pollution usually was local at a certain area and often tended to be heavy within that point source. Okay? And the problem resolution to that, or the way to address it, which the EPA and a number of other government agencies did, was to reduce these direct discharge, these point sources. And we've done a pretty good job of that over the last 50 years. So if we skip ahead now to the present day, our main source of mercury is again this atmospheric, which is a non-point source in a way. We know where it comes from, but where it ends up, we can't really trace it back per se. That's our major issue with it now. And if you look at the pollution level and where it occurs, it tends to be sometimes in remote areas, as I mentioned. And it can be light and moderate at any one point in time, but over time it's cumulative. So it can build up over time and be a significant problem. And the solution to that, or the resolution for it, would be to reduce emissions. And the technology is there for coal-fired power plants to put scrubbers and things in place, and these scrubbers go on top of the smokestacks, and they remove that ionic mercury before it's released in the atmosphere. The problem with that is it's very expensive for the plants to do, and there was some language back a few administrations ago in the U.S. that removed some of that from the Clean Air Act, so they're not required to put these scrubbers on coal-fired power plants. So speaking of coal-fired power plants, if you look across the U.S., each of these dots represents a power plant, and then the size of the circle represents the amount of mercury that was emitted from each plant, reported back in about 2010. And you can see just from the distribution of this that this is really a Midwest problem, right? And most of these power plants are located in the Midwest. Texas, never to be overdone. Texas produces a lot of mercury. So it's kind of interesting if you look at where the mercury, or where the power plants are, these mercury emissions. And as you might guess, if you look at the atmospheric deposition of mercury, this is, I guess it's not showing up. This is actually wet deposition up here. And they measure this with special samplers. They're like funnel traps. So rain falls into the trap or snow, they look like the bottles on them, and they can go sample that water and measure mercury. And so they can measure that wet deposition. And that's what this is. It's a distribution of wet deposition across the U.S. So the darker colors, there's more, and then the lighter colors, there's less. And it's interesting, if you look at, it shows the same general distribution, but a little bit different. Some of the higher areas, areas of highest deposition, tend to be a little bit more east and north of where we saw our power plants. And that's attributed mostly to the jet stream and the movement of the atmosphere in that direction. From the Gulf, moving things to the north, and then the westerly winds to the east. What's interesting from this standpoint too is if you look at the distribution along the eastern coast, the south, and we overlay that with fish mercury advisories in the country, you can see that currently we have a statewide coastal mercury advisory all along the eastern seaboard into the Gulf of Mexico. We don't have anything like that on the west coast. And we also, if we look at the New England states, just about all the New England states and the central upper Midwest, all of these states have statewide advisories for fish mercury. They get tired of putting up signs for a particular lake, so they just call it a statewide advisory, and they have information in their fishing handbooks as to how many fish, which fish you need to be careful about eating, and those kinds of things. The states in yellow, which we are one of them, it doesn't mean that we don't have an advisory, we just don't have a statewide advisory. But I suspect in 8 or 10 years we probably will. We have about 20 lakes right now that have advisories on them. And these signs and posts are getting expensive because every year we add about 5 more lakes to that list. So anyway, you can see it kind of parallels where you see a lot of that wet deposition. So with regard to aquatic foodlets, how does that mercury that's in the environment, positive from the atmosphere, end up in fish? And there's an interesting process when it's deposited either on the landscape or even on the surface of the water, this ionic mercury. Most of the action occurs in lake settings, so areas that are flooded for prolonged periods of time. You have plants that die, a lot of organic matter becomes anoxic, and these methogenetic bacteria are responsible for methylate. It's a certain class of bacteria that convert this ionic mercury to methyl mercury. So what it does is it just transfers by adding a methyl group here, and that's what we call methyl mercury. Unlike elemental mercury, it's this methyl mercury that's the issue for us, for fish, for other animals. And the reason is because there's a methyl group here, it's very lipophilic, meaning it likes fats, dissolves and readily binds to fats. And you can imagine that if you're consuming that, it's going to bind with fats and proteins. So this methyl mercury makes its way into the aquatic food web like this. And just as with many other contaminants, as it works its way up different trophic levels, it becomes accumulated in greater concentrations. We call this bioaccumulation. So by the time it reaches the top predator, their mercury concentrations tend to be much higher than what you might see in zooplankton. And of course, we're in this part of this food web too, and we like to call ourselves the top of the food chain. In some cases, that's not good, right? We eat fish, especially big fish. But keep in mind, even though we are at the top of the food chain, in our opinion, we don't always have to eat these fish. We can eat fish lower in the food web. And I'll talk about that in a little bit. So methylmercury in fish, we used to think it came from respiration, that they absorb the mercury in the water through their gills. And while they do absorb a little bit, most of it, nearly all of it, comes from what they eat. So you are what you eat in that case, and most of it comes from the diet. And the other thing about fish that is a little bit unique compared to mammals and other animals is they eliminate mercury very slowly, almost negligibly. So they just continue to build it up. And as they get larger and older, that mercury concentration increases with the age and the trophic level of the fish. So most of it comes from what they eat. With regard to us, it also comes from what we eat, and that's why we're concerned about mercury in fish. And if you look at human health risks, I'll just put a caveat out there. When we talk about putting mercury advisories out, or warnings, and explaining the health hazards of eating mercury, we're always concerned about the segment of the population that's most susceptible to it. And that would be unborn children, young children developing their nervous system, pregnant or nursing mothers, women of childbearing age. So everything that we're going to talk about with regard to the advisories is very conservative in the sense of we're trying to protect that segment of the population. Somebody like me, my nervous system's it was fully developed years ago, and I think it's on the downhill side because it's a neurotoxin. We're concerned about it. Although we And I don't mean to say any of this to scare you, because I'm going to come back to this, the few people that eat 2 fish meals per week. We'll see how everything kind of works out. But with regard to human health risks, there are some very significant issues with methylmercury because it is a neurotoxin for us. It can lead to, for developing nervous systems in children, fetuses. It can lead to impaired cognitive development, memory issues, language, all of these things. So we need to take it very seriously, and that's why we monitor as well as we do. And again, it's this segment of the population that we're really trying to protect with advisories, what we call a reference dose, EPA standard of how much you shouldn't eat X amount of mercury per day, and I'll tell you what that is in a little bit. Back in the early, must have been 2001, 2002, the EPA and the US FDA got together. Before this time, it's like every other government agency. The FDA had their own regulations on what mercury advisory should be. The EPA had theirs. But they got together and actually produced a very important document that was sponsored by the Natural Resource Council. And one of the key conclusions, and I just want to point this out, was in this joint advisory, fish and shellfish are an important part of the diet. So they're pointing out the importance of eating fish and shellfish and how that can contribute to heart health because of omega-3 fatty acids that are in fish, and also to children's development and growth. So one of the key conclusions from this mercury work was not don't eat fish, be careful about eating fish. It was actually make sure you're eating the fish. But they did have some recommendations. The top 3 of these were very specific to certain types of fish. So one of these recommendations was to avoid shark, swordfish, king mackerel, and cuttlefish. That's good for us, because I haven't caught any of these fish. These are our big 4 that we're always concerned about. But you can buy these in the grocery stores and along the coast. If you look at these fish, these are all top predatory fish, high up in the food chain, so that's why they have elevated mercury concentrations. And I'm going to add another one to this in a minute. You don't have to worry about that one either, unless you can afford it. So there is some information about which fish to avoid. And again, one of their recommendations was eat up to 12 ounces of fish or shellfish, and that's an average meal is 6 ounces, so that's 2 meals a week. You should be eating fish and shellfish that are low in mercury. Okay? And then finally, if you're unsure, you're fishing and harvesting fish yourself, you're not sure what the concentrations are, there's lots of information in just about every state now. There are fishing handbooks, or online you can find information about fish health advisories. So it's all out there, and they can give you advice. And if you can't find any, the advice is just to limit consumption to 1 average meal per week. A lot of information out there on this. The EPA's webpage, they have some interesting stuff for the public. It's explained very well. Everybody can understand it. Here's these top 4 fish that don't fish, right? And then the do fish, we don't even list them all. I mean, this is just a smattering. The do fish are many, many, many fish. So anyway, you can see what's out there on that. All right. Here's our top 4, and as I mentioned, I'm going to add one more. I'm going to add tuna to this list. And I'm not going to add the tuna that you're thinking about. I'm going to talk about bluefin tuna. Because bluefin tuna, one of the largest species of tuna, is a top predator. The problem with bluefin tuna is the cost. The market value of bluefin tuna now in Japan, if you go to a sushi restaurant, a meal of bluefin tuna, 3 pieces of sushi is going to cost about $110 US. So if you can afford that, have that. It's a good thing. Most of us don't have to worry about that, right? A few years ago, and I forget, maybe it was 2010, one bluefin tuna came into the Tokyo market and sold for $250,000. That's crazy. All right, this is the tuna I want to talk about. You've all had this and probably eaten this. But there's two types of tuna. I don't know if you've ever noticed when you go in the grocery store, there's this chunk white tuna, and then there's what we call solid white albacore tuna. Anybody know the difference between these two cans of tuna fish? Other than the labeling?
The bottom one's tastier.
Cost. It's a little, light tuna. Everybody wants to think of calories in the diet and stuff. That's really probably not it. The difference, though, is this chunk white tuna is actually skipjack tuna. It's not, and while it's in the tuna family, it's not technically a real tuna. It's much smaller fish. They feed lower in the food chain, but they can call it tuna. Whereas white albacore tuna actually are a tuna, a larger tuna, higher up in the food web. So they feed different things than skipjack tuna. And because of that, if you look at the mercury concentrations in these two, they're quite different. So a can of light tuna has about 0.12 parts per million. And I'm also going to mention the omega-3 fatty acids. A 6-ounce can of this is about 240 milligrams of omega-3. White albacore tuna, if you look, almost 3 times as high, 0.3 parts per million. But about 800 milligrams of omega-3 fatty acids, so quite more, a lot more omega-3 fatty acids. For me, for the amount of tuna fish I eat, I would much prefer to have this in my diet rather than this, but you can see the differences in the two. And I want to come back, I'll come back later and I'll put things in perspective just so you can get a grasp for, am I eating too much tuna fish? Am I not eating enough? We'll do an exercise there. All right, so there's our high mercury fish with the addition of bluefin tuna. And I just put a smattering of things here. This list could go on forever, to be honest with you. What we call lower mercury fish. And you can find this a more extensive list in the EPA documents and stuff online. But one of the things I always like to point out is things like catfish. People always think about catfish as bottom feeders and eating all the pollution. Oh, they're all contaminated. No, they're not. They're one of the cleanest fish out there. They're just ugly. So. But anyway, scallops, all of your shellfish, shrimp, those type of things tend to be low in mercury. Salmon, trout species generally are low, much lower mercury concentration. So you can see there's a lot of things that we eat where we really don't need to be concerned about mercury concentration. The problem is when we talk about mercury in fish, there's lots of things that are low in mercury, and then our top 4 plus the bluefin tuna, which we say, oh, avoid these fish, they're high in mercury. Well, most people just come to this conclusion, well, oh, fish have mercury, I need to be concerned about it. And while that's true, it's creating probably more of a problem for people maybe avoiding eating fish because of this, which in my opinion is more of a problem. So you need to weigh the risks of eating fish for a healthy diet and omega-3 fatty acids versus weigh the risk of what you're eating with regard to mercury concentration. And there's enough information out there to help guide that decision. All right, so let's come a little closer to home. These were average mercury concentrations of fish in South Dakota back in about 2005 when we were working on this, one of the projects. And as you might expect, northern pike are a top predator in our lakes. They tend to have the highest mercury concentrations, about 0.5, about 0.6 in pike. And then some other top predators, bass and walleye, white bass. And then it declines pretty precipitously after that. A lot of our panfish are relatively low. And the EPA guidelines for being concerned about fish and putting up a fish advisory is about 0.3, and that's a very conservative. So in cases where the fish are down here, they wouldn't even recommend putting up a fish advisory. So when the fish exceed that 0.3, they recommend to the states to put up an advisory. EPA can't mandate that, they can only make the recommendation. This is from our 2016 fishing handbook, and as I mentioned, you'll find this kind of information in all the states. Maybe it's on the web page, maybe it's in their handbooks. But it'll give you the lakes where we have the advisories posted. And you'll see these advisories, they're white signs, they're posted at boat ramps or entrance to the lakes. They'll tell you what species have the advisory. And in our case, we post an advisory when we see mercury concentrations of 1 part per million or higher. So that's pretty high. And again, that's an old FDA guideline. It's different a little bit than the EPA's guideline. But what we don't have, at least for the general public, is the actual concentrations of mercury in the fish, because there would be information overload there for that. But it's enough information to help guide your decisions on where to fish, or where to fish. So with that as kind of some background, the work that we did in the early 2000s was focused primarily on walleyes, because walleye are a bread and butter fishery in the state. And we wanted to try to figure out some of the factors that affect accumulation of mercury in walleyes. So this is kind of an outline of 4 things I want to talk about today. Some of the work that we did here. Also how mercury concentrations vary seasonally and by sex in walleyes. The effects of mercury on walleye reproduction. Just as with us, it's a neurotoxin to walleyes and it affects the reproduction. We'll talk a little bit about that. And then finally, kind of want to wrap up with some of the management options that we might have. It's with anything, we're always trying to manage around the problem that we have until the problem can be resolved. But there are a few things in our toolbox that we can use to help manage around this issue. So here are mercury concentrations in walleyes for a number of lakes. All of these lakes are in the eastern part of South Dakota, primarily in the northeast, the Prairie Coteau. And you can see we got quite a range from Pelican Lake, which is up by Watertown, all the way up to Bitter Lake, which is just north of that, near Wapay. The distance from Pelican Lake to Bitter Lake is about a 45-minute drive, so these aren't lakes that are scattered all over the Prairie Coteau, but they're relatively close. So it's interesting why we see such large differences in mercury concentrations of walleyes, and that was one of the questions we had with our research a few years ago. And we've always known that when we create or construct a dam and we build a reservoir, that there's been these reservoir effects. So all of that flooding, you're flooding all of this landscape where that atmospheric mercury, the Hg2, might be deposited into the plants from the soil, and you flood that, and you create conditions for those methanogenic bacteria to methylate mercury. So this flooding can be very important. And we've known that's been the case with reservoirs. And we kind of suspected that might be what was happening in the Northeast. So this is a Landsat imagery of eastern South Dakota, although you might not recognize it this way. But this is a Prairie Coteau. This is Lake Ponset, Lake Thompson, Whitewood, Wapay, all the lakes in the Northeast. Back in the mid to late 80s, we were experiencing a drought. So you can see there's not that many lakes, some small seasonal wetlands, semi-permanent wetlands here. But in the mid to late 90s, we had successive years of high water in the state, so everything flooded. And we're still seeing that today. Right? So if you look at the same area in 2000 from the Landsat image, you can see all these lakes, large lakes that were formed from flooding that didn't exist back in the 80s. So that reservoir effect is kind of noticeable there. And we were able to use Landsat imagery, and we could digitize the area of these lakes, the same lakes, and ask the question, well, is mercury concentration in fish related to the change in surface area of the lakes? Now, because some of the lakes didn't expand because they have an outlet, so the water just kind of went the outlet. And other lakes don't have an outlet, so they expanded pretty dramatically. And when we looked at that, we saw this. This was the mercury concentration in walleyes as a function of the change in surface area of the lake. And while there's a little bit of variability here that's unexplained by the change in surface area, there was a generally positive relationship between that and mercury in fish. About 62% of the variability explained that. So we thought that had a big influence on what we were seeing in the Northeast with regard to elevated mercury. Some of the other things we were working on at the time was trying to help with the monitoring aspect of it. Does the time of year you sample mercury in walleye affect the concentration? Does it vary across seasons? And then how does it vary between the sexes? So here's some data from Bitter Lake, and you can see we sampled, these were age 3 walleye that we sampled in summer of 2006. So it was the same year class of fish. But if you sampled them in spring, early summer, the mercury concentrations were significantly higher than they were at other times of the year. So went back in July. And from a monitoring standpoint, we typically go out and we're sampling fish for mercury analysis in late summer, part of our standardized sampling. So if you're sampling here, you're not going to detect that 1 part per million. I drew a line here, so you wouldn't post an advisory in this lake if you were sampling fish at that time of year. If you would have sampled in May, they exceeded that 1 part per million, and you would have to put an advisory up. So it was important at the time of the year be considered. The question is, why does it vary? Do these fish actually have less mercury in them than these? And the answer to that is no. They have more mercury in them. Okay? And I'll show you why. The reason that they decrease when we look at the concentration of mercury in the fish is because the fish are growing. So if they're growing faster than they're accumulating mercury, that concentration goes down. And if you think about an example of perch here, 150 gram perch in the winter growing to 225 grams by the summer. And then if we add the mercury burden, the burden is just how much mercury is in the fish. So let's say we got 45 micrograms of mercury in this fish. And that's increasing over time to 55 grams for these fish. But if I calculate it as a concentration, so I'm dividing 55 by 225, you can see the concentration is actually going down, even though this fish has more mercury in it, if you ate a whole fish. It'd be bigger fish. But. So it's a little misleading, but the whole thing is related to what we call this growth dilution effect. The other thing that we learned was that males and females are different. And fish too. But from a sex standpoint, female walleyes, when we looked at the size of the female walleye relative to their concentration, you can see that it's lower as compared to males. So an 18-inch female from Bitter Lake had about 0.6 micrograms part per million versus maybe about 0.8 for a male walleye. And the reason for that is if you look at the age of a male walleye versus a female walleye, that's 18 inches. The male walleye is about a year older. Okay? They're just growing slower. And what that means is that the male fish has been in the environment longer, so it's had more time to accumulate mercury. But that's hard information to because walleye aren't dimorphic, meaning that you can't tell a female and a male if you're catching them. So we can't really give information to anglers about what is it before you throw it back as a male. So it's a little tricky, but it does help us understand, one, the relationship between body size and mercury, and that we can do something about, and I'll mention that. All right, we'll go back to our lakes here. These are the lakes in northeast South Dakota again. And I want to talk a little bit about the effects on walleye reproduction, because there's some pretty interesting stuff that we found that was going on there, and consistent with what we were seeing in lab studies. So we had this opportunity to study these two lakes on the end of our spectrum, Pelican Lake, which is by water tank. And the interesting thing about this is that Pelican Lake has very good natural reproduction of walleyes. And in fact, for many years, we used Pelican Lake walleyes as root stock for spawn to strip their eggs, fertilize them, took them to Blue Dog Fish Hatchery where we raised them, hatch them out to fry. And then we would stock fry from Pelican Lake walleyes in the Bitter Lake. Because in Bitter Lake, we don't have very good natural reproduction. We like to stock it every walleye fry. So we were doing that. So anyway, we wanted to compare the fish in these two lakes to see what was happening with regard to reproductive physiology. And this is just kind of a template for what some of the hormones in walleyes concentrations look like through time. And then the bottom graph here is gonads, so this would be for a female, just to be the eggs. And if you look at the eggs as a percentage of the body weight, a female walleye typically this is pre-spawn, up to 16% of their body weight can be all eggs. And they spawn, they release the eggs, of course, it drops. But the patterns in estradiol, testosterone look something like this. Female and male fish would have both of these hormones, but these are females patterns. You can see post-spawn that the levels tend to be low. They remain low throughout the summer. And then in late summer, early autumn, these estradiol concentrations go up because it's a precursor to egg development. So they're building up these eggs this time of year and into the winter, so that by next spring, they'll have some eggs to release. Testosterone is the same way. This is kind of a pattern of male fish that it's high in the spring during spawning, and then post-spawning, testosterone levels in males go down, and they start to build up again in the fall. Same thing, their testes are building up, gaining mass. So let's take a look at what, and well, I mentioned, we can measure this by taking blood samples from walleyes, non-lethal samples, and then we look at the plasma. So these are plasma concentrations. Essentially. So here's what we found in female walleyes in Bitter Lake and Pelican Lake. Pelican Lake is the lake with low mercury, and Bitter Lake is the high mercury. So if we look at estradiol on female fish, they're pretty similar through spring and summer until late summer. And you can see that Pelican Lake is much higher, significantly higher than they were in Bitter Lake. And then we look at eggs, gonad productions, percent body weight. We don't see much of a difference in the summer into the fall, a little bit here, although we didn't project it through the whole winter. But by the time spring rolls around, you can see that Pelican Lake fish have about 16% gonad weight compared to about 12 in Bitter Lake females. So while 4% doesn't sound like a lot, if you look at it in terms of how many eggs are being produced, for an average 4-pound female, that's a difference of about 40,000 eggs between these two. The other thing we did this in the lab. We were looking at how mercury might affect fertilization rates, because there's some evidence that mercury concentrations or mercury in the environment can affect sperm motility. It binds with enzymes and things in sperm that reduces their fertility. So we were able to set up some experiments where Trevor's adding eggs and I'm adding milk. So we're doing fertilization externally as fish do, but in petri dishes instead of living. And then we could just go back and incubate them at 4 degrees, and then 24 hours later look at how many of the eggs were fertilized, and we look at the cleavage furlough. The presence of this furlough kind of indicates that fertilization occurred. So we can just count fertilization success. And here's what we found. We had 5 different treatments of methyl mercury concentration that we made. And in the 0, you can see fertilization success was about 60%, which is pretty well within the range of what we see in other studies. But as mercury concentration, even at this first very low level, you can see a very significant drop in that fertilization success. It stays about the same until you get to a really high concentration that drops even further. And to put things in perspective, we measured methyl mercury concentration in Bitter Lake from the water, and it was almost 0.001 here. So we could expect this kind of decline in just fertilization success for the fish. The other thing that was interesting, this is more of an intrinsic thing, so this is associated with the fish themselves. If you looked at fertilization success for the males from Bitter Lake, the high mercury males, versus the males from Pelican Lake, the low, you see that even across these treatments, consistently the Pelican Lake males had higher fertilization success than the Bitter Lake. So again, some evidence that mercury is affecting reproductive physiology of the fish. So in a nutshell, the 2 things that we kind of concluded from this was that the concentrations in the fish themselves, in the cases of females, we see reduced steroid levels and lower gonadal somatic indexes, related to mass. And then in the males, we see reduced fertilization success. But in the environment, because fish fertilization occurs externally, methyl mercury concentration in the water is important by affecting what we think is sperm motility in males that also reduces fertilization success. So it's kind of a double whammy. All right, switch gears, and now let's talk a little bit about some options. So we're trying to manage around this issue. We have 20 lakes now with mercury advisories on them. What can we do from a management standpoint, other than putting health advisories up and those sorts of things? So we thought about this a few years back, and we thought, well, what if we, we're stocking Bitter Lake anyhow. We're stocking them with fry, and the fry spend 2.5 years, all of their life, before they're a harvestable size fish out there. So what if we were actually to stock fingerling fish, larger fish, from lakes that aren't contaminated with mercury? They would spend less time in the environment to become harvestable fish. and maybe their mercury concentrations would be low. Right? Or what if we could get our hands on some H1 fish? These would be about 250 milligram fish. Stock them. By the time they're harvestable size at 2.5 years old, maybe they would be having a lower mercury concentrations. So when we first thought about it, we were going to do a very time and labor intensive mark, stock, recapture type thing. We would introduce fish from other systems into Bitter Lake, but we'd have to mark them, we'd have to stock them, a lot of them. We'd have to come back and sample them periodically through time, see if the mercury concentration. Because I like to do things the easy way, which is some good and bad sometimes, we decided that we would try to model this. And we, in my lab, we do a lot of bioenergetics modeling. So part of this, you can do the same with contaminants as you can with just trying to estimate food consumption. So I won't go into it, but basically we're able to use the physiological energy budget of the fish to estimate its mercury consumption and ultimately how much mercury is in the fish after a certain amount of time. So I got to give a plug to Dave here, it's a selfish plug. For the last couple of years, we've been working to develop some new software, Fish Bioenergetics 4.0, and we just completed it, I think, depending on my email this afternoon from Dave. But we're very close with it. Dave was instrumental in setting all this up and keeping it going. We've been around the country, a couple of different places this year, giving workshops and stuff on it. But it's kind of cool. It's very user-friendly. We got about 105 species of fish in the model, so succulent species. And you can do all kinds of simulations and modeling on growth and food consumption. But we also have some sub-models built in to do contaminant accumulation, so we can actually model mercury concentration in fish. So let's see how this all works. If well, I'm going to be consistent here. The lines in the green is observed mercury. This is what we actually measured in the 2005 year class of walleye. So we started sampling them in August 2005, and we tracked them for about 2.5 years until September 2007. So these are the actual mercury concentrations of the fish, and then the dashed line represents the size of the fish in terms of grams. So by the end of 2.5 years, these fish were about 560 grams. They're growing. This is one of the fastest growing walleye populations in the state. It's pretty fast growing. But a couple things I want to say about just this. If you look at their growth rates during the first year, basically, and the mercury concentrations in the fish, they're pretty parallel. Not too much more, but what happens after the first year into the second summer life is you see the growth rates increase dramatically. And because of that, you see, because they're eating a lot, you see the increase in mercury concentration. What's happening here is that they're making a switch primarily to prey fish. So they're eating, at this size, eating primarily benthic invertebrates and things, a few small fish. By the time their second season comes around, they're large enough to capture other fish like yellow perch and fatty minnows, and they grow like crazy and have higher mercury levels. All right, so we tried to model this. We took the same fish, fed them the same diet, so we knew what the diets were, we knew what the mercury concentration and the prey were, we measured all that. So we modeled it with our bioenergetics model. And you can see for the first year, we did pretty good. It predicted mercury concentration. Then after that, it just blew up. It was close. And we started thinking about this, this whole switch to fish, even though we had fish in the diet here. One of the biggest unknowns in any energy budget for us or fish is activity levels. We don't know how much activity the fish are experiencing. But when they switch over to feeding on fish, their activity levels go up. It takes a little bit more activity to chase fish around. So we know that for walleyes, that activity level ranges in between 1 to 3 times their metabolic rate. So we just kind of used those as bounds and then did an optimization procedure to try to calibrate the model to it. And what we ended up with was a much better model that tracked mercury concentration of fish at the time, much better than our vision model. And it's got a variable activity level between, just optimize the fit between. So anyway, now that we were here, we could take our model and simulate different conditions. Like what if we could stock some fall fingerlings, these fish have about 24 grams. What if we could stock them in late summer with a 0 mercury concentration? see how they track through time, from the time they're harvested to what mercury concentration is. So that's what we did. These are stocking of these H0 families. So we're starting off at 0 concentration. And you can see, at least for a few months, they're remaining lower. But by the time the first year rolls around, the second spring, they've pretty much caught up. And when they do catch up, they just track fish. So stocking fish at this size, with that mercury concentration, really there's no advantage to it. And people have asked me a few times over the years, why, with this difference here, why aren't these lines parallel through time? It makes sense that they would be, right? So why are they catching up here? Just kind of staying at a lower level. Well, the difference is if you look at the actual burden of mercury in the fish, so micrograms of mercury. Now, I model for these fish, this is the mercury concentration, even though they started at 0, that's what they had eaten at the end of day 1. So their concentration at the end of day 1 is 0.112 micrograms. That's not a concentration, I'm sorry, it's the burden. This is how much mercury is in that fish. For the same size fish, what we saw in the lake was about 2.9 micrograms. So the difference between these two is 2.78 micrograms, the difference in burden. Well, that 2.78 micrograms also is maintained here, it's maintained here, here, and here. The difference is by the time you're up to 100, 200, 300 micrograms, that initial burden difference of 2.78 is meaningless. So they catch up very quickly, and the bottom line is they're just eating so much and growing so fast, and they're eliminating mercury very slowly. They just catch up very quickly. All right, our second simulation, so if we were to stock big fish, these would be bigger fish the following year, this is kind of what we got. You can see they still catch up rapidly like the H0 fish did. And by the time they reach a harvestable size fish in September, really not much of a difference. And I suspect if we could model it out even further, they'd ultimately just catch up. So we didn't have to go through this exercise of stocking fish and monitoring through time. We could just look at it like this and decide not to do it. All right, so one of the things that we can do, though, this is the size, walleye size here, concentration for bitter lake fish. Years back, when we were doing our work, we had a 16-inch minimum size limit on walleyes bitter lake. So you're basically forcing anglers to keep only fish that are bigger than 16 inches, which would tend to be fish with high mercury concentrations. So since that time, we've removed that. So now there is no minimum size limit on walleyes. And we know from experience that anglers generally start to harvest walleyes when they're 12 inches, 13 inches. They'll start to take them home. So they're able to take home fish that have a lot lower mercury concentration than what we had is in terms of the minimum size. And that's something that we can do from an enhancement standpoint to help remedy some of this. All right, so what is the challenges for us? I mean, there's a number of them. In terms of consumption advisories, the approach for that obviously is to protect human health, put the information out for everyone to know, make decisions. From a fish management standpoint, again, I view this as we're always monitoring around or managing around the problem. We haven't really fixed it, but we've got to creatively come up with ways to manage around it. So monitoring, improving our monitoring programs, regulation changes, things that we can do to try to offset some of the mercury exposure. But the big gorilla in the room, I would say, is emissions reduction. Decreasing mercury emissions from power plants is the big and until we are able to significantly make headway on this, we're still going to deal with this issue. So what do? Do we eat fish? Do we not eat fish? Everything eats fish. Just to alleviate some worries, I don't want to be a scare tactic of mercury in fish, but I also want to make sure that everybody walks away today with understanding how important fish are in the diet. So if you look, there was one study done back in the early 2000s that looked in the U.S. at blood mercury levels in children and women. And I won't read all this, but just some of the highlights here. Measures of mercury exposure in women were generally fall below levels of concern. About 8% of women had concentrations higher than the EPA's recommended concentration. So overall, in the United States, our culture, inclusion of fish in our diet, generally falls below any level of concern. But there's still some segment of the population that's concerned. So, are you eating too much fish? I want to, this reference dose is the US EPA puts out 1.1 microgram per kilogram. And I've got tuna fish, tuna fish, walleye, northern pike, all with mercury concentrations. Here's what it looks like. Anybody eat more than 12 cans of tuna fish a month? All right, so you're good. What about 10 meals of tuna fish per month? 4 meals of walleye, maybe? 2 meals of northern pike? Especially in the wintertime. So that's, you gotta spread this out. You can't look at it as a day, you gotta spread it out over time. I prefer to spread it out over 6 months. And the reason is, unlike fish, we actually eliminate mercury. The half-life of mercury in humans is about 45 to 90 days. So a half-life of 90 days, it's 180 days, I would have eliminated all the mercury I had if I start off with that third in my body. So it's a little bit better way to spread it out. So now, answer these questions. So Brian, do you eat in 6 months maybe more than 15 meals? So about 23 meals a while. So this one, it's going to be spread out to a year. You really do eat 147 cans of tuna. I mean, you can. That's even at this most conservative reference dose. This is what you can eat and still be way below any concern. So are you eating too much fish? I would argue that you're not eating enough. So just some advice, and I'll wrap it up here. Michael Pollan, if you've never read this book, Omnivore's Dilemma, it's a cool book. I recommend reading it. He talks about human diets and our omnivorous patterns. Eat food, mostly plants, and not too much food. And I'm just going to steal, plagiarize from him, and extend this to fish. Eat fish, mostly small ones, and not too much. And since it's Friday, you should be able to find a fish fry somewhere. Otherwise, that's all I had. Go ahead, thank you.
Thanks, Steve. I think we have to probably wrap it up. The other class will probably be in here in a second. So please talk to Steve if you have any questions.
Yeah, I'll hang out here with Colin.
Thanks, everyone.